this video, I want to look at what happens if we apply a conservation of energy approach to the simple harmonic motion example that we've been working with so far. So to do that, we need to recall a couple of things. First, recall that the potential energy stored in a spring is 1/2 kx squared. If we're saying that the spring is deformed by some displacement x, and this isn't necessarily doesn't strictly apply to a spring. It could be anything that has any sort of elastic stretch to it. And then we will recall that kinetic energy is equal to 1/2 mv squared, which of course we could rewrite in terms of x as 1/2 mv x dot squared. So these two forms of energy can get put together, and by conservation we can say that the potential energy plus the kinetic energy is equal to a constant. Now, what's useful about this is that if I substitute in my equations such that I have 1/2 kx squared plus 1/2 mx dot squared and say that that's equal to a constant, and then if I divide through by 1/2 m, so I'm going to divide it out here, and if I divide a constant by 1/2 m, that's just going to be some different constant. What I end up left with is an equation of the form x dot squared plus omega n squared x equals a constant. Now, recall that omega n squared is equal to k over m. So if we look back here and say, well, omega n squared is k over m, and I just divided by m over here, all of a sudden I have an equation in this form that looks a lot, or is starting to look a lot, like my standard form equation for simple harmonic motion. The only difference here is that it's integrated one level from my equation for simple harmonic motion, where simple harmonic motion involves x double dot rather than x dot. So we're pretty close to having the same thing. So what this means is that if I can take the derivative of this equation, and get a new expression, that will give me some relationship that allows me to pull out my natural frequency from my standard form equation. So I'm going to go ahead and take that derivative. Now we do have to be a little bit careful here because we're looking at this equation, it's in terms of x, and I want to take the derivative with respect to time. And we have to remember that x itself is a function of time. So if I'm taking the derivative of something which is itself a function of some other variable, I need to make use of the chain rule. And the chain rule basically says that if I take the derivative of a function of x with respect to time, where x is a function of t, then this is equal to the derivative with x of t inside of it, the derivative of the function, multiplied by the derivative of the function. So this is the chain rule that I'm going to make use of to take this derivative. So if I do that, I'm going to get the derivative first of this first term in my equation, which is k, pulling out the constant, 1/2 k, pulling out the constant. Now the derivative of x squared is 2x, and now I need the derivative of x itself, so I'm going to put x dot. For my next term, I would get 1/2 m, pulling out my constants, 2 x dot, and now taking the derivative of the function itself, I get x double dot. And my last term on the other side of the equal sign is just a constant, so if we take the derivative of a constant, we get 0. So I can see that my 1/2s cancel. This one with this 2, and this 1/2 cancels with this 2 right here. So now I'm left with k x dot plus m x dot x double dot equals 0. I can see that I have a common term in here of x dot, so I'm going to pull that out. X dot multiplied by the quantity kx plus m x double dot equals 0. Because I have the 0 on the right hand side of my equation, I can divide x dot out, and then I'm going to rearrange and write this in the form x mx double dot plus kx equals 0. So now looking at this, this looks very similar to what we saw for simple harmonic motion. And again, if I take my substitution, taking my natural frequency and plugging this in here, I get an equation of the form x double dot plus omega n squared x equals 0. Substituting this in there. So all I've really done is re-solved for my standard form equation. And the reason that this again is useful is because all I had to do to get there was take my energy, recall that by the conservation of energy, energy is constant, take a derivative of it, and I got my standard form equation. So as long as I can come up with an expression for my total energy, take its first time derivative, and arrange it into the form of the standard form equation, I can use that to pull out my natural frequency for whatever system I happen to be dealing with. All right, thank you.